Hydroelectric generators give us about 20% of our renewable energy. The potential energy in gravity is transferred into kinetic energy as it flows through the tube and eventually into the pool. The turbine will typically spin either the magnet or the coil. This creates an electrical current that can then be sent out to power various items. And there you have it, basic hydroelectricity. Our machine uses these same basic principles in order to convert kinetic energy into electric energy. But first we need to know more about how electric energy works.
I have a pipe.
Yeah.
Do you want to hold it? Do you know what it's made of?
Metal? Is it brass?
Copper.
Is copper magnetic?
No.
Uh-oh.
I'm gonna go no, I didn't think it was.
I'm gonna go yes.
Yeah.
Well, why don't we check? This is a magnet, and I'd like you to use it to test whether the copper is magnetic.
No.
I want you to be 100% sure here. What do you think?
No.
It's not magnetic.
I said so.
Okay. Is there anything in there?
No.
What do you see in there?
That's nothing.
So why don't we drop something through it, just make sure it's empty, right?
Okay.
This is not a magnet. So this isn't a magnet, but let's see what happens when we drop it through. That was a dull experiment, wasn't it?
Yeah.
Yeah.
Okay, so what's gonna happen if we drop this magnet down the pipe? It's gonna pull through. Pull through. Let's do it. 3, 2, 1.
That was weird.
That's well cool.
Took longer.
What's slowing the magnet down?
It's got to be magnetic poles or something. I don't know, north, south.
Something to do with the polarity of the north and the south poles.
But it doesn't stick.
But then it's not magnetic, so it shouldn't do anything.
Right, you guys saw that.
That is slightly magnetic on the inside somehow.
It's going to be magnetic inside, isn't it, or something? Does it like...
Kind of tilts. I think it's the powers of the universe.
I don't know why it's doing it.
Well, this is what's exciting, is only a few blocks from here was the lab of a guy called Faraday.
In October 1831, he built the world's first electric generator here, a magnet which you push and pull in and out of a coil to generate electric current.
So that's the actual...
Yeah, for world's first electric generator.
And there's a permanent magnet in the middle?
That's a permanent magnet, yeah.
It was Faraday who realized that it's a changing magnetic field that actually can generate electric current. So as the magnet is falling through the pipe, it's creating a changing magnetic field that generates little electric currents, so-called eddy currents in the pipe, and they create an opposing magnetic force on the magnet, slowing it down. So it actually turns the pipe into an electromagnet,
I see.
which pushes the magnet up. And this is what's known as electromagnetic induction. So it causes my LED to light up there. But it's important that you move the magnet quickly, because if you move it too slowly, the magnetic field is not changing fast enough to generate enough voltage to light this LED. This is actually the way all electricity is generated.
Is it?
Yeah, you move a magnet near a conductor and it creates electric current. But where is this electrical energy coming from? You can't get energy for nothing. Well, Faraday realized that there must be a force pushing back on the magnet. It's the same force that slows this magnet down as it falls through the pipe. So there's actually energy being converted from gravitational potential energy into electrical energy and eventually to heat. So this pipe is warming up by taking some of the energy out of the falling magnet. Is that any good or what?
Oh, it's very good.
Electromagnetic induction either creates direct current or alternating current. Direct current is found in power supplies like batteries, and alternating current is found in power supplies like our generator. In order to calculate the energy regarding our machine, we need to talk about Ohm's law and electromagnetic equations.
In this video, I want to present the concept of voltage, and to do this, I'm going to use an analogy with water. Let's take a garden hose that's showed in green, and at the end of the garden hose, let's add a nozzle that restricts the flow of water. At the left end of the garden hose, let's have a piston. Now let's ask what happens when I push the piston to the right. Well, what's going to happen is we're going to get a water flow out the nozzle. This water flow is analogous to the movement of charge or current. This restriction that the nozzle causes in the water flow is analogous to electrical resistance. It resists the flow. This piston on the left side exerts a pressure on the water that forces it to the right. The pressure caused by this piston is analogous to electrical voltage that we'll call V. Let me erase this. Let's continue with our water analogy. The green shows a pipe that's filled with water. This orange shows a water pump with a handle that we can crank. And the harder we crank this pump, the more water flows within this pipe. Now here we have a restriction in the pipe that reduces the flow of the water. And this we'll call resistance R, electrical resistance in the analogy. Let's say that we crank this pump. We cause a certain flow. And this pump is analogous to voltage in a circuit. It creates an electrical pressure that causes the current to flow. Now, as we crank this, we could say we crank with 1 volt. We're turning it kind of slowly. Now, as we speed up cranking it harder and harder, perhaps we crank it at 2 volts of pressure and we get an increase in flow. We crank it really hard, we have 4 volts of electrical pressure, and the current flows even harder, even more. In electronics, we would call this a circuit. We have a source of energy, we have a current flow, and we have a resistor load. If we were to draw the electrical equivalent of this circuit, for the pump, we would have a battery. This is the symbol for a battery. This is the plus terminal, this is the minus terminal. And the pipe is like a wire. And at the right side, we have a resistor. This is a symbol for resistance. And we have a wire connecting the resistor to the bottom of the battery. So the electrical equivalent is resistance R. We have a current flow in this wire. We have a voltage that exerts an electrical pressure that causes the current to flow in the circuit.
The final equations we need to talk about are force, power, and other kinetic equations.
Force is a push or pull upon an object that causes it to move. Force is measured in newtons. A newton is the amount of force required to give a mass of 1 kilogram an acceleration of 1 meter per second squared. In this example, we see force being placed upon a spring. Energy is the ability to perform work. There are 2 categories of energy: potential and kinetic. Potential energy is energy which results from an object's configuration or position. Kinetic energy is energy which an object has by reason of its motion. When a force has been applied to a spring, for example, the spring gains potential energy. When the applied force is removed, the spring returns to its original state, thus releasing kinetic energy. Work is the amount of energy transmitted by a force. In this example, the work being done is the amount of energy it takes to compress the spring. Work is measured in joules. A single joule is the energy expended by a force of 1 newton moving 1 meter along the direction of the force. Knowing the amount of energy required to compress the spring tells us how much work is involved. But that is not the whole story. If we can also factor in the amount of time it takes, we can calculate a quantity known as power. Power, then, is the rate at which work is done. This in turn means that power is the rate at which energy is transmitted. Power is measured in watts. A single watt is the rate at which work is done when an object is moving at 1 metre per second against a force of 1 Newton. The formula for calculating power is P equals E over T, where P is power, E is energy, and T is time.
This is an example of an equation having to do with our hydroelectric generator. The first thing we did was cut off the base of the jug. Next we had to cut holes in the jug. The copper wire coils are 50 wraps each. Going around the CD, each coil is alternating between clockwise and counterclockwise. We then glued and taped the CD to the jug so that it would stay firmly in place. Then we glued the wooden paddles to the foam core. The foam core, wooden pole, and magnet CD are all held in tightly together by rubber stoppers. That way, when the water pushes on the paddles, the CD moves. As a final touch, we made our paddles double wide and added duct tape to solidify the hold. When tested, our new design produced about 26 amperes and the old design produced about 23. The first test we conducted was whether 4 paddles would be better than 8. The average output for 4 paddles was 17 amperes. The average output for 8 paddles was 35 amperes. Therefore, 8 paddles was more effective than 4 paddles. Because this experiment is highly reliant on gravity, we decided to test whether 30 centimeters, 65 centimeters, or 100 centimeters would be a better height. The 30 centimeter gave a very low output of 0.01 amperes. 65 turned out to be 32.20 amperes. But overall, 33.97 amperes for 100 centimeters won out in the end. We then tested whether 50 or 100 wire wraps per coil would be better. 50 wraps average out at about 45.7 amperes. 100 wraps average out at 80.2 amperes. It clearly won. We then tested pressure by poking a small hole in a soda bottle. 5 centimeters of water went 0.5 inches, 10 centimeters of water went 3 inches, 15 centimeters went 4 inches, and 20 centimeters went 4.5 inches. This showed that more pressure equals more force. And that's our hydroelectric generator.